All right, so today we're looking at some applications of these rational functions. A lot of these questions they're pretty basic and stuff, but it's tricky to get them set up, of course, like any word problem. A lot of these are very possible questions that you could see on like an SAT or ACT type test. The first type of rational function that you usually have are your, like, we call them work rate questions. It's a question that goes like this. If Fran can clean the garage in 3 hours working by herself, and it takes Angie 4 hours to do the same job working by herself, how long would it take them if they clean the garage together? How long would it take to clean it together? So again, if you just had that question and you were asked it, there'd probably be a couple different things you would try to figure out. The easiest way to do it is to set it up using a rational functions. So here's how we set it up. We say that if it takes Fran 3 hours to do the work, okay, then she does 1/3 of the work each hour. That kind of makes sense, right? 3 total hours, then after 1 hour, she's done 1/3 of the work. Okay, it takes Angie 4 hours to do the work, so again, after an hour, she's done 1/4 of the work. Okay, how long will it take if they help each other is something that we don't know, so we use an X down there and we say that, you know, together in 1 hour they would have done X part of the work. Okay, so we set it up kind of like this. We do Fran's 1/3 of the work, Angie's 1/4 of the work, and we say that that's, if we add those together, that's going to equal how much by themselves. So if you look at this now, this is a super easy rational function to solve. Remember, you have to find common denominators. A good common denominator here would be 12x. Okay, so a couple things here. I just multiplied by the 12x to clear it all out of the bottom. You can make those common denominators first and then cancel them out. Like this one, you would multiply by 4x on top and bottom, this one by 3x on top and bottom, this one by 12. You cancel out your denominator, you're left with something that looks like this. So 7x equals 12, so x equals 12 over 7, or it take them 1.7 hours. Okay, so those are pretty basic. There's not too many other versions that I could give you of this, unless I told you that, like, together they can complete it in 2 hours. How long would it take this one by themselves? So that would be kind of the same thing, except your x would be somewhere over here. Okay, for some reason the trickiest ones, but the most like applicable real life ones, are when you're talking about like rate. So for example, currents or speeds going in opposite directions. The first type are when we're going like with the wind or a current and against the wind or a current. So first thing, the big equation, and you've been using this equation for a while and you should know it, that distance equals your rate times your time. Okay, so a big question that I like to ask people here, you know, like if you're going, let's say 60 miles per hour for 1 hour, how far have you gone? Okay, well, you'd be surprised the answers I've heard for that, but if you're going 60 miles per hour for 1 hour, then you've gone 60 miles. If you go 60 miles per hour for 2 hours, you've gone 120 miles. So you can keep using that ratio right there. You could also write it a couple different ways, either solving for rate or solving for time, kind of depending on what you're looking for. Okay, so this is a typical current question, okay? He can row 5 miles per hour in still water. So in the still water, that's his typical speed, okay? It takes him as long to row 4 miles upstream as 16 miles downstream, okay? A couple reasons for that. You have that current working against you. So you have to think about it a little bit. When you're going upstream, okay, you're swimming, or you're going upstream means the water, right, is going this direction, and you're in your boat, this is a lovely picture, trying to go this direction. Okay, so if your normal speed is 5 miles per hour, okay, and you're trying to figure out what the current is, so you kind of got to pay attention to your question here. Are you looking for the current or are you looking for your speed? In this case, I'm looking for my current, so you're going to kind of set it up using this table right here. Okay, so I know that x is my speed in still water, so I can set it up going upstream. Okay, that's my speed in still water, 5 miles per hour, minus the speed of the current, because that's subtracting. Okay, whenever I get down here and I've gone my 4 miles and then I'm coming back this way, then the speed of your boat adds to the speed of your current, okay, giving you an equation 5 plus c. You also know your distances, that was given to you. What do you know about your time in this case? Well, if it takes you as long to go 4 miles upstream as 16 miles downstream, then that tells you that your two times are going to be equal to each other. So whatever this is going to equal this one. So the way we're going to do that here is we're going to use what time is. So time, again, coming back up here to these equations, is distance divided by rate. Okay, so I'm going to take my distance here, and I'm going to divide it by my rate. And since it's the same, they're as long as, then I can set those two ratios equal to each other. Okay. After that, again, this is just a rational function. You're going to multiply this one by what this one doesn't have. So that's a 5 plus c. This one by 5 minus c. That makes your common denominators. You can ignore that, and you can solve, and you get the current is 3 miles per hour. Okay. It didn't ask you how long that time actually was. You could figure that out. It only asked about the current. Okay, so these were already set up for you. Let's look at doing some ourselves. So again, a boat goes 240 miles downstream, and the same time it goes 160 miles upstream. So again, think about your water. Draw a picture if you need to. It says the speed of the current is 5 miles per hour. So this is a very similar question, except this time they've given you the speed of the current. They want you to find the speed in still water, or your x. Okay, so if the speed of the current is 5 miles per hour, then you know that one of these is going to be x plus 5, and one of them is going to be x minus 5. Okay, that's just your current. Add your current, subtract your current. So think about this a little bit. Which one is going to be 240, and which one is going to be 160? Which one is upstream, and which one is downstream? Okay, so remember, downstream the current adds to your speed, so this one's going to be 240, this one's going to be 160. From there, you just solve. I don't think I'm going to finish solving that. The answers are at the bottom of this page, though, so if you want to do your work and be sure you can check your stuff, that would be great. All right, kind of same thing here, except we're talking about an airplane, so very similar thing. An airplane flies 910 miles with the wind, and the same time it can go 660 miles against the wind. The speed of the plane in still air is this. So remember, this is your x. You're looking for c, or the speed of the wind in this case. Okay, so again, both of these, this time the 305 goes at the front, minus x, and 305 plus x. And you just got to figure out, again, which one is upstream, which one's downstream. Okay, so this one, remember, is against the wind. The wind is subtracting from your speed. So this is going to be your shorter distance, the 660. This one, the wind is adding to your speed, so it's going to take you further, 910. Again, you can solve it from there. I'm not going to do it. Again, answers are at the bottom of this page. Same question here. Again, swimming. You should probably try to set this up yourself first and then solve it, but I'm going to go ahead and do it for you. A person swims 11 miles downriver, and the same time they can swim 7 miles upriver. Again, the speed of the current is 4 miles per hour. So again, you're going to have your x plus 4 and your x minus 4. Okay. Again, downriver, upriver, which one goes where? Okay, remember, downriver, the current pushes you. Upriver, the current stops you. Again, you can solve that and check your answers. These last two are work questions, very similar to the first one. You should check that out and see if you can do it first. But remember, if Kent can paint a certain room in 6 hours, then in 1 hour, he's done a sixth of the work. If Kendra needs 4 hours to do the same room, then in an hour, she's done a fourth of the work. I want to know how long it's going to take them working together. Okay, again, common denominators and solve. I'm not going to finish that for you. But same thing here. They can build a laptop twice as fast as Cliff. Working together, it takes them 5 hours. So this one's a little bit different. You know that together, they've done a fifth of the job in an hour. Okay? Marco can build the laptop twice as fast as Cliff. Okay, so this gets kind of tricky. One of these is going to be 1 over x. One of these is going to be 1 over 2x, right? Because it takes them twice as long. Okay? The tricky part is that if Marco can do it twice as fast, you're wanting to tell me that this is Marco, but that is not true. Marco is going to be the shorter one, right? You know, like if that was a 2, then he's done half of the job, and the time it's taken him 4 hours. So this one's going to be Cliff. Okay, just a little side note there. Again, find your common denominators and solve. Remember, when you do that, x is going to give you Marco's time. 2x would give you Cliff's time. Okay, if that makes sense. Cool.